Hello guys. So this is Prashant from MyLearnCube. So we are going to start the lecture series on digital logic design. From gate point of view, this subject ranges from 4 to 6 marks, and our approach will be to cover the previous year gate questions, and also for every topic we will try to include as many examples as we can. So the whole lecture series will be examples and questions oriented. First of all, it will be examples oriented, and very important point to note down, these lecture series are self-paced. If you are getting into some trouble for some topic, you can pause the video, you can replay the video, you can give some time to yourself to learn those things, and just try as many questions as possible. Just pick up questions from web, from some coaching manuals, anything. Just do as many questions as possible. Even at the end of the lecture series, we will provide you a question bank for all topics. So the syllabus we have divided into three parts. One is introduction, in which we will cover these topics along with the previous year questions, and then we will cover some combination circuit. This is also some easy stuffs, adder, subtractor, multiplexer, and so on. And then we will cover a bit trickier topic, sequential circuit. So in sequential circuit, we will start with basic flip-flops, how they work, how their characteristics tables built, and once we will master these things, then we will see how these basic flip-flops are used to construct large sequential circuit, just like counter. And we will see the different type of counters. Okay, so logic gates. Logic gate is nothing. A gate is nothing but a very basic or fundamental unit, electrical unit in a circuit, which take, suppose, so this is out of box. So this is a black box which takes some input and will generate some output. Okay. So as you all know, there are gates like NOT gate and AND gate and so on and so forth. So I will not waste a lot of time on these basic stuffs. So I will try to finish it or wrap these simple topics in a quick session. So just see what is fan-in. Fan-in is, suppose this is a gate, AND gate. The number of inputs connected to a gate is called fan-in. And then what is fan-out? Don't get confused. Fan-out is not the number of output. Output is always single. There is single output coming out of a gate. So it's not like the number of output is called fan-out. Fan-out is the number of gates to which this output is connected. Suppose there are two gates. This output is connected to gate 1 and gate 2. Hence, the fan out of gate 3 is 2. Fan out of gate 3 is 2. Similarly, as you can tell, the fan out of gate 4 is only 1, since it is connected to G2 as an input only. Now see basic gates. There is a NOT gate. As you all know, it inverts the input. You will take 0, convert it into 1, take 1, invert it into 0. Again, you can see the AND gate. What AND gate will do? It will just, for AND gate, I would like to design a circuit. You can see from here. Okay. So this is a bulb. This is A, this is B. Suppose I am just start the power, and for current to travel this path, and from source to destination, the current has to take this path, this path. So for current to reach from source to destination, both these switch has to be on. Otherwise, the current will not flow. That means when both A and B is 1, only then the output is 1. Only then this current will blow up. Otherwise, if either of A or B is 0, the output is 0. Very simple. Similarly, OR gate means the output is 0 if and only if both inputs are 0. We can also see this also with respect to a logic circuit. Okay. See this diagram. Suppose this is A, this is B. Now the current, if current is passed to reach this destination, the current can either flow this path or this path. That means if either A is 1 or B is 1 or maybe both are 1, then the current will flow. That means the output is 1. Otherwise, that means if both A and B are off, or if both A and B are 0, only then the output is 0. So this is OR gate. Now the very important gate is XOR gate. It is sometimes also called special gate. Why? You will see in the later slides the application of XOR gate. You will find the application of XOR gate almost in all combinational circuit. So one more thing, though it is not important from the perspective of gate, XOR gate is the lowest power consumption gate, lowest power supply it requires as compared to AND gate, OR gate, NOT gate. XOR chip requires the lowest power for its running, for its working. So two input XOR gate. XOR gate is nothing but exclusive OR gate. It's exclusive OR gate. That means exclusive OR. Either of A or B should be 1 for output to be 1. That means either A is 1, that means at that time B has to be 0, or B is 1, at that time A has to be 0, then only Y is the output is 1. Or in layman language, in some students learn this gate as when A and B are different. You can see when both A and B are different, then output is 1. Actually it means when either A is 1 or B is 1, not both at the same time, then only the output is 1. Otherwise output is 0. Now very important point to note down, when any of the input is 1, when any of the input is 1, output is the complement of other. You can see from here, when B is 1, output is the complement of A. So that means if someone asks you to implement NOT gate using XOR gate, then you will simply do this thing. Just make one of the input is 1. If this is A, then definitely output is A bar. So you can see some truth table or some questions on that. So when any one of the input is 1, the output is the complement of other. Similarly, there is a gate called XNOR gate. It is XNOR gate, means output is 1 when both inputs are same. It is opposite of XOR gate. It is sometimes also called coincidence gate. Coincidence means when both are same. When both are same, only then output is 1. Okay, I forget one important thing. For XOR gate, we represent XOR gate this way. Or in simplification form, when A is 0, A bar means A is 0 and B is 1, or A is 1 and B is 0. This is your output equation. For XNOR gate, it is represented as A XNOR B. This is the equation for output of XNOR gate. So for XNOR gate, you can see when any one of the input is 0, when any one of the input is 0, output is the complement of other. Output is the complement of other. From here you can also see when any of the input is 0, when B is 0, output Y is the complement of A. So again, if you want to implement NOT gate using XNOR gate, then you will just put 0 on one input, give when A, suppose A is the another input, then output Y will be the complement of A. So these are the 5 basic type of gates. Now there is a gate questions. This has been asked in gate and it is very easy also. So what is the relationship between XOR gate and XNOR gate? And from this question we will see one very important concept also. So Majority of you will answer that okay, XNOR is the complement of XOR. Majority of you, but this is wrong answer. How? We will see. We have already seen that XOR and XNOR, yes, they are the complement of each other. But in what case? This is partial story. In what case? When number of inputs, when number of inputs is the number of inputs are even. That means we have already seen, suppose A, B, so this is A XOR B and this is A XNOR B. See this table, 0 0 0 1 1 0 1 1. So XOR gate will give 0 1 1 0 and XNOR gate will give 1 0 0 1. So okay, from here we can say that XOR is the complement of XNOR. But see, if we will implement this concept when the number of inputs are odd, that means solve this first and then we will try to find its relation with respect to these gates. Okay, suppose the next take this one, 3 input XOR gate. For 3 input XOR gate, it's A, B, C suppose, then A XOR B XOR C. From here you can see 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So if you want to calculate the XOR of this, so you can, this is fairly equivalent to this. That means you first take XOR of first 2 input, then the result you XOR with this. So A 0 XOR 0 is 0 and then 0 XOR 0 is 0. 0 XOR 0 is 0, 0 XOR 1 is 1. And doing this will give you this output. You can check. Now solving this one, 3 input XNOR gate in the similar fashion. Suppose I am making now is XNOR gate. How will it proceed? A XNOR B XNOR C. 0 0 XNOR is 1. 0 XNOR 0 is 1 and 1 XNOR 0 is again 0. 0 0 1 1 1 1 0 1 0 0 0 1. And when you solve this way, you will get the, and shockingly you can see, suppose this is Y and this is Z, you can see Y is equal to Z. That means if, now the point is, now you can make this as a trick. If number of inputs, if it is even, then XOR is complement of XNOR and vice versa. But if number of inputs are odd, then XOR is equivalent to XNOR. So what is the correct answer for this question? Both 1 and 2. XOR and XNOR may be equivalent if the number of inputs are odd, may be complement of each other if number of inputs are even. Great. Now the universal gate. Universal gates, there are 2 gates. One is NAND gate. NAND gate is nothing but complement of AND. That means not of AND. You can say not of AND. So in case of not of AND, not was when both were 1, only then the output, AND was when both were 1, only then output was 1. But it is just complement of and truth table. So when any of the input is 0, you can treat it's like when any of the input is 0, the output is 1. Similarly, for NOR gate, it is not of OR. That means when any of the there in OR gate there was, when any of the input was 1, the output is 0. Output was 1. So here in NOR gate, when any of the input is 1, the output is 0. Otherwise, the output is 1. So why they are called universal gate? They are called universal gate because we can implement any gate using NAND gate. I be it a NOT gate, NOR gate, XNOR gate, any gate we can implement using NAND gate. So that's why it is called universal gate. See an example. This is what? Your NOT gate. So how will you implement NOT gate using NAND gate? Very simple. So this is your A. Again, in NAND gate, if you will see, it is the equation is y is equal to A dot B bar, because it is the NOT of AND. If you will apply De Morgan's here, then you will get A bar plus B bar. With De Morgan's law, you will get this one. Again, similarly, this is NOT of OR. That means A bar dot B bar. De Morgan's second law. So here it is going A. It is going A. Then A bar dot, sorry, A dot A bar, and A dot A, definitely A and A bar. Similarly, that means you can apply, you can implement NOT gate using NAND gate. Similarly, if someone asks implement AND gate, so you already know NAND gate is not of AND. If you apply one more NAND gate here, so it is already not of AND, not of AND. And if you apply one more NOT gate here, so it will be not of and this NOT will cancel out, it will give AND gate. Similarly, if you want to implement OR gate using NAND gate, what is the equation of OR gate? Achha, there is one trick, not a trick, there is a concept. How to generalize it? This is the equation of your OR gate. So all you know inversion law. A inversion of means A bar to the power bar is A. This is inversion law. So I can write this way. This is equivalent to A plus B. So implementing or applying De Morgan's law in inner bar will give us A bar dot B bar bar. Here is the trick. We got it. So A bar we will get this way. B bar we will get this way. And actually this is what? AND of this. And above is not. So it is exactly the form we require. This is your OR gate. A or B. I think it is very clear. Now suppose implementing NOR gate. Implementing NOR gate or no, yes, it's implementing NOR gate using NAND. With the same trick, NOR you all know A plus B bar to the power whole bar. You all know. Okay. So OR you have already seen. How to implement OR? This is your, this was the OR. Just implement one more NOT gate, it will become NOT of OR, which is nothing but NOT. This way you can implement any gate using this universal gate. Okay. So in similar fashion, you can see NOR as universal gate. NOR as universal gate. You can see how to implement this. I will try to solve one for you. Suppose I want to implement this one. Not this one. This is easy one. Take some hard one. Okay. Take this one. NOR as AND. And you all know is A dot B. Just again our previous trick. A bar plus B bar bar. That's it. Solve. This is A bar. This is B bar. And this is A bar plus B bar to the power bar. So this way you can implement any gate using NOR gate. So that these NOR gate and NAND gate are called universal gate. We have already discussed these concepts. So now there are two assignments for you. First, try to implement NOR, XOR and XNOR using NAND gate. I think I have already told you this one. So try to use XOR gate and XNOR gate using NAND gate, and once you implement this is just for practice. Try to implement XOR gate. This is actually gate question. Try to implement XOR gate using XNOR, using minimum number of NAND gate. This question has been asked in gate previously, I think 2 or 3 times, that how many NAND gates, minimum number of NAND gates are required to implement XOR gates. So we will discuss this question and answer in the next lecture. So just try to go through the whole lecture. We will come up with some questions and new concepts in the next lecture. So one last concept from the basic gates is bubbled gates. Bubbled gate means it's nothing new. It's just bubble. Whenever you show bubble, treat it as a, or take it as a NOT gate. Very simple. This is nothing but, if you want to see it in detail, so you will see this is something like this. Actually this bubble is nothing. This bubble is also a NOT gate. Bubble is not. So there are some, these are some analogy. However, this is not there is no requirement to mug up those things. You can just calculate, okay, this one is A bar and this one is B bar, and you are applying A bar dot B bar ka bar, which is nothing but A. If you apply inverse De Morgan's law here, you will get A plus B ka bar to the power bar, which is nothing but A plus B. So it is equivalent to OR gate. So no need to mug up those things. So guys, so here I'm going to end this lecture. In the next lecture, we'll try to solve some previous year gate questions, and we'll see some more concepts which may help, in fact which will help us in future